Welcome back to the lecture series in bioenergy. So, today what we will do, from the basic mechanism, now we will see the output of it, and from there what are the strategies which are being followed. So, let us enumerate the features of the crops which will could be used for producing new biomass. Okay. Coming back to the slide now. Now, we will talk about what all features are we looking forward to. So, we have two options. So, if we talk about any kind of energy crops, so they could be either grown in the land or in the water. So, when we talk about crops here, I include everything. Okay. I am not really so it includes plants, trees, algae, and several other things. Okay. So, land or the water, and within the water it could be whether it is a marine, salt water, which is a huge resource, or is it fresh water. Okay. These are the two things. Similarly, for the land, utilizing waste and fallow land. Or resorting to vertical farming. Okay. This is the first thing. Second, now among this, first, what is the yield? Yield with respect to time. So, whenever we talk about a yield of a crop, you can either look what is this much quintal per hectare or likewise. That is one aspect, but there is another aspect. How much time does it take? A crop which takes, say, 10 months, 12 months, is a long period, whereas as contrary to it, a crop which takes 6 months or 3 months is much more faster. So, in terms of the yield, we have to keep in mind what is the time window are we talking about? How much time does it take for us to get the complete yield of that crop? Step 1. So, okay, yield with respect to time, step 1. Second, point B out here, what is the, so of course, we will look for yield with respect to time, maximum yield with respect to time with the shortest time. Okay. This is very critical. So, there is always a trade off between these two. Second thing, reduction in energy input to produce. What does that mean? So, this means in order to grow the crop, we need fertilizers, we need water, we need land, pesticide, insecticides, and so on and so forth. So, lesser are their use, so your energy input will be less. So, we have to look for those crops among that whole series of things what we mentioned earlier, the ones which consumes least amount of energy. Okay. Now, point C. Point C is we have to look for the crop whose cost is less in terms of, again, this is directly linked to, because there are crops, say for example, we talk about sugarcane and all these crops, they are very intense. They need a lot of fertilization. You cannot grow sugarcane in every place. And there are several other crops which are not really domesticated yet, but they grow very fast and they could have a very interesting fuel production profile. So, what in other word I wanted to say is, like, sky is the limit. We may need to really go through the genome of different wild species of grasses which we never explored, and they grow very fast in the wild. They have certain very specific features. So, if you look through, like say for example, through thousands of years of evolution, we have domesticated a handful of plants. Say for example, you have domesticated rice, we have domesticated wheat, we have domesticated maybe a little bit of a barley and some of these sorghum, maybe a few millets. But if you look in the wild, if you walk through in any grassland or anywhere, you will see there are so many different kinds of grasses, and maybe they haven't been analyzed. We really do not know. So, what is most important, that we have to look into this subject with a very open mind, that we should not get tied down, okay, we only have this handful of crops, from there only we have to really. There are so many fodders, we do not even know. There are so many fodders which are being growing in the wild and which are palatable to the cows and something, which we just never really looked into that. So, as more and more we are understanding the genome and other things, we simultaneously also have to look for the wide variations of the grasses which are growing in the wild. They may grow in any fallow land, they may grow in wasteland without using much of the resources in terms of fertilizer, in terms of pesticides, and those could be a very profound source for biomass. So, this is a food for thought to think. There are so many species of grass and it is worth looking at each one of them, and if we could do some kind of a breeding studies on them, or if we could do some genetic manipulation in them by which we can manipulate some of their starch, cellulose or hemicellulose, or you can reduce the lignin. We will come to this part, what I meant by all that thing. Okay. So, but just keep it in mind, do not kind of stick your brain with the fact that okay, we just have handful of this. We have many more. It is just we have to look carefully into the nature, we have to explore nature, then only we will be able to appreciate this. Okay. So, this is the second point in terms of the cost, because this is very important. Always remember that in terms of the petrol, in terms of the diesel, in terms of the coal, what all fuels we are currently using, or even in terms of the nuclear power, these we got free of cost, because mankind never had to invest a single cent or a dime to produce those. Nature has produced them. Nature has produced radioactive materials, nature has produced coal, nature has produced gas, natural gas. Mankind has only done two things. First, they discovered that these could be utilized as a fuel, their flammability. Second thing, what mankind has done, they bored whales in order to extract them out. That is the only cost mankind has given. But here in the current world, we are thinking differently. We are now trying to emulate nature itself. We wanted to produce fuels for ourselves. So, this is a different route. This is not something. So, the economics comes very clearly, that whenever we talk, we are flowing in a way, biomass, bioenergy and like. But the fact is, we are entering into a domain whose economics have never been done to the last decimal, that exactly, because there is a lot of investment what we have to do, and it is a socio-economic problem, because you cannot use any land. As I am repeatedly telling you, this is a big issue. Many a times, many program fails just because you have to compromise with the food production, which you cannot do. Okay? So, coming back, so this is one of the issues which will be very important. Coming back to the slide in terms of the cost, next point which is critical out here is the composition. So, composition of the biomass. In terms of the composition of the biomass, we will come here. There are several issues linked to it. So, whenever we talk about the plants, let us take a standard example of plants. You have cellulose, you have hemicellulose, you have lignin. Okay. So, let us talk about it a little bit. Okay. You have cellulose, hemicellulose and lignin. Now, these three things are present in plant at varying proportions. So, the most of the plant has the cellulose is at the highest concentration, followed by hemicellulose, and the third thing is the lignin after that. So, in terms of their chemical nature, if we talk about, so they have different kind of chemical nature. So, cellulose, typically cellulose makes 40 to 50%, this is in the woody plants, whereas 20 to 40% is the hemicellulose, rest is all lignin. And if we talk about the cellulose, cellulose is basically a glucose polymer, it is a linear chain of glucose. Linear chain of glucose. So, something like this. And this chain is attached to each other by, if you remember in one of the previous lecture, I told you by 1,4 glycosidic linkages. So, they have 1,4 glycosidic linkages and average atomic molecular weight is around 100,000. Okay. And they are one of the most prominent component of the plants. Then comes the hemicellulose. The difference between cellulose and hemicellulose is, this is a very mixed polymer. It is made up of glucose, mannose, and there are a bunch of 5 carbon carbohydrates which are present there, xylose, arabinose, then you have methyl glucouronic acid, then you have galacturonic acid, so average molecular weight is less than 30,000, and instead of linear in the case of cellulose, this one is a branch chain. So, this is the critical difference. It is a very branch chain structure. So, it will have possibly 1,4 as well as 1,6 linkages, which I have already discussed to you during photosynthesis. Okay. And these hemicellulose are bound tightly but non-covalently to the surface of the cellulose, tightly, but this is very important, but non-covalently. Why this is very important? Bound tightly but non-covalently to the surface of cellulose, because realize one thing, that what are we extracting in the form of bioenergy? We are breaking the bond energies. So, between 2 carbon there is energy which is holding them, between carbon nitrogen there is energy which is holding them, in carbon hydrogen there is energy which is holding them, like so on and so forth. So, there is a bond. there is a covalent bond, somewhere is electrostatic bond, whatever, So now the thing is, what you are doing essentially, you are breaking that bond. You are breaking that bond, and the energy which is released is the one which you are utilizing for XYZ function. So in the form of hemicellulose and cellulose, the binding is non-covalent. So there is no covalent bonding. It means if you split them, the energy which will be released will be much less. So that is why it is very important. You should understand what kind of bondings are there, and of course it will be easy to break them apart, because there is hardly any strong bonding taking place. Okay. So next thing is the lignin. The third category in this A is the lignin. So lignin is very similar to these families, but it is chemically similar to cellulose and hemicellulose. It's kind of a binder, chemically similar. It's a binder for the cellulose, between the cellulose and hemicellulose, and putting it all together. It is amorphous, and it is made up of 3 carbon chain. 3 carbon chain, this part is very critical, 3 carbon chain attached to the ring of 6 carbon atom. Attached to the ring of 6 carbon atom, and this is called, there is a name for this, and this is called phenyl propanes. And based on this, there is a classification. Coming to that classification, we go to the next page for this classification, classification of lignins. So phenyl propanes, from phenyl propane I am continuing, these may have 0, 1 or 2 methoxy groups. Okay, attached to the ring. Attached to the rings, giving rise to 3 structures, 1, 2, so Roman 1, 2, 3, into 3 structures. One, 2 and 3. It is very interesting to note these 1 kind of lignins are present in the grasses, 2 is present in the woods of conifers, and third kind of type 3 is present in the deciduous woods. Okay. And very interestingly, there is another aspect of lignin, which is the smallest of all of them. Lignin, when you burn lignin, when you are burning the whole thing, its decomposition varies, and we will come in further detail on this one, varies from 160 degree to 900 degree centigrade, and it generates a lot of solid residue, and approximately 40% solid residue it generates, especially during pyrolysis. What is important here, now coming back, so we talked about, we have what is the cellulose, what is the hemicellulose, and what is the lignin content. So lignin content, if the lignin, so what you are doing, you are taking the residue and you go through what we will be learning after this will be you go through the pyrolysis process and breaking them, decomposing them. Now there are a specific temperature at which the bonds breaks. Say for example 100 degree centigrade, 200 degree centigrade, 300 degree centigrade. So, lesser temperature the bond breaks. Listen carefully. Lesser the temperature at which the bond breaks, you will be needing lesser energy. So, if something breaks at 50 degree, you hardly, almost little higher than room temperature. If your room temperature is say 27 or 30 degree, or maybe in a summer 45 degree, okay, 40 degree, fine. If something breaks at 50, you just have to raise the temperature and it will break. So, you need very less energy compared to something which breaks at say 100 degree. Then you have to boil something at 200, you need to give more and more energy. But now the problem comes when you have a material which is a mix of something which is burning at 200, something at 300, and another one, a component which, whose range is from 160 to say 100 to 900. So, now the problem is when you have such material, so when the wood is coming, just see this picture, so you will realize. Say for example, you have a piece of wood coming. Okay. So, you have three component here, say lignin, yes, hemicellulose and cellulose, and you are processing the whole thing together. And if I say the cellulose decomposes at say 300 degree centigrade, I am just giving a number for you, I mean do not take this number because we will talk later, and say this one happens at say say around 250 degree centigrade, but whereas this one has a range from 100 to 900. Now, see the situation. Technically, just by 300 you should be able to get the necessary decomposition of these two, but because there is lignin which is in between, it is there, you cannot degrade the lignin. So, what you will be getting out of this will be a product which is not fully decomposed. It will have a lot of contaminants of lignin, and lignins, half burnt lignin or whatever, So, keep that in mind. These are very basic fundamentals what you have to keep in mind. So, that means you love to have crops which have lesser concentration of lignin, but then it has its own set of problems. It is not so easy that if I just want, I can, because these have evolved over the ages and nature has done every molecule. So, that is why it is being always said, and coming to the slide, this is being always said, cellulose to lignin ratio is critical. Cellulose to lignin ratio. This ratio determines what will be the efficiency of decomposition and how much energy we really needed to spend on it. So, this is very critical for you people to understand that cellulose to lignin ratio will further determine, point E will be, so that is why I had to go to the contaminant point, composition with least contaminant, composition with least contaminant See for example, some of the species have lot of alkali metals and all those. So, and they have lot of issues with it. And F, we have already talked about, they should have low, these crops should have low nutritional requirements. We have already talked about it, nutritional requirements. So, that is why we may always look for, search for grasses growing in the wild. There are a lot of grasses which are growing in the wild with least care. They hardly have any nutritional requirements and they grow. So, if we could adopt some of them and try to grow them in fallow land, wasteland, and transform them for energy production, or there are a lot of bio waste which we could use, like the banana peel, it is a waste Could you utilize it? There are so many crop residues, so many fruit residues. When you eat orange, the orange pill, okay, the mango, you remove the cover. Could you use them? These are the territories. Or say for example jackfruit, it has a huge thick covering, no one explored it. So these are the kind of things how we Indians have to think, that how you could really make a difference. There are so many ways, but only you need to know how to process them. We will come to that. Now, having said this, let's enumerate after this, coming back to the slide, let's enumerate after, once we have talked about this, the factors determining the conversion process. Okay. So, we have talked about how we are going to select the crops. Now, we will talk about the factors determining the conversion process. Okay. So, we will resume from here in the next class. Okay. Thank you.